Hey again. Sorry, I didn't include the part of the video where I showed you the pictures of electric field within the presentation, but you can take a look at that on your own, really. This simulation might do a better job. Again, the concept of electric field is one that says, okay, we have a real electric charge somewhere. What is a positive charge going to do if we place it in space around that charge? So let's just think of this one at a time. Let's say we place a real positive charge in space somewhere. We say, all right, well, what's a test positive charge going to do if we place it in space somewhere in this system? Well, it's going to want to be repelled away from this positive charge. Like charges repel. Okay, fine. So that means the vector field, the electric field, is going to be drawn away from this real charge in all directions. And the way this simulation represents the field is it makes these arrows, these vectors, bolder if the electric field strength is stronger, and then faded out as it gets weaker. Obviously, the field gets weaker as we get farther and farther away because the electric force also gets weaker as we get farther and farther away. The negative charge gives us a similar picture, but with an opposite effect. If we place a negative charge in space, well, again, if we were to then place a test positive charge anywhere in space around that real negative charge, it's going to want to be attracted. So the vector field is represented as arrows going radially inward from all directions towards that real negative charge. Okay, fine. This is just really another way of saying that our like charges repel and our unlike charges attract. But things get very interesting when you put more than one charge in a given space. Let's say we have a real positive charge and a real negative charge in space near each other. Well, now the vector field looks kind of interesting. Again, this is all with respect to a test positive charge. What would a positive charge do if it were placed in this space? Well, if we place it somewhere over here, it's going to want to try to go towards the negative and away from the positive. If we place it, say, right here, it's going to want to go this way initially, but then kind of wrap around back toward the negative because it's attracted to it. The field lines are representative of what the positive charge will do, and they start to get really weird the more and more real charges you add to the system. This representation of electric field lines is one you'll be using well, very much with your electric field hockey lab. That is the simulation that I'm treating as your final assignment for this week. Um, as long as you can boot up the simulation, you'll see field lines like this, and your goal will be to guide a positively charged hockey puck through an obstacle into a goal. I do hope you enjoyed. In fact, it's my favorite simulation on the PhET website, which is the same website I'm using now. Um, Obviously, if you have questions about anything, you can post your questions on that spreadsheet, and I will answer them as soon as I can. You can flip back to the presentation if you wish and go through the individual pictures of the fields. And then there is also an equation for electric field for the Regents students. It's the exact same equation as Coulomb's law, except we're only dealing with one charge at a time. So instead of being KQQ over the R squared, we just take away a Q. This is the equation for electric field. And then we just change this to an E. Electric field is the K constant multiplied by the charge in question divided by the distance between the charge and the point you're interested in squared. Again, electric field is just it's a representation of how strong a force would be. It's not a force, it's just a ratio between force and charge. That's why if you flip to the slide itself detailing the electric field equation, it tells you right there the units are newtons per coulomb. And again, here's the equation. It's the same as Coulomb's law. If you throw one of the Q's away, you only calculate electric field at a point, one charge at a time. I do hope that these videos helped you understand the topic of electrostatics. There are more resources if you check out the outline. And obviously your textbook is a resource as well.